Okay, yes, I believe we are recording again. All right. So here's a good question. When it comes to questions about IPC, interpractice communications, let's hear a really good one. Can we hear the one that we heard during the break a bit?
Okay.
All right, how does it go again? The
Okay.
question about IPC.
Oh, how they communicate with each other?
Right, so you asked me about
Yeah, is there a
process.
is there a process that communicates to other processes? Like there's a separate process for doing that.
Okay, great. So now here's how I want to go about handling that question. There's a couple of different ways to actually do this whole thing, right? So when I heard about um, the nature of IPC, there's a really good book called Unix Programming, the Unix Programming Environment, or Networking Unix Programming Environment by W. Richard Stevens. Unfortunately, he passed away. I think he had like a successor, Ralph Rago, who like kept up his books a bit, but um, the different methods. They are enough to, I guess, write a bit of a book on, right? So here, let me just show you exactly what the nature of the, I guess you could say, different options for handling multiple process communications are, right? So just going to share my other browser with you so you can see it too. Uh, so technically in the operating system, it's going to have its own resources, but for inter-process communications, right? Um, you can do it by means of networking in the operating system itself, believe it or not. There's actually, let's see, the green one that I have here at home is the inter-process communication one. And if I could just pull it up and show it to you, you'll see that, it's it's a bit lengthy, the subject. So how it's handled, let me just put in here IPC. How it's handled could be through a variety of ways, right? In the, that's not good, but in the operating system, right? The operating system may have its own API for making that happen, but also there are certain, uh, I guess you could say, language libraries that also do the same thing, right? Let's just take a look. Do they have the actual, not necessarily. I wish they did have the actual ability to look through them. Um, if if there is a, you know what? Let me do you a quick favor. I'm gonna actually grab the book right now and then like tell you the um some of the actual topics that they get into just for this one subject. And then after that, we kind of like, take a look at what certain libraries do, right? So here goes. Let me just put in a small pause here. Okay, so let me get to answering your question. Pause, and it was supposed to have pause. Okay, so I guess that outtake is in there for me reaching for books and whatnot. It is what it is. At least I look prepared. Um, so let me just get back to I was doing the screen share. Everybody's seeing the screen share. All right, here's the actual book itself, right? Yeah, I know it's kind of mirrored network programming. Um, the topics that he actually goes over, I'll tell it to you this way. Just the indices or the borders of the book have dozens of different functions for handling this whole thing. Some of it is Unix based, but some of it's actually P threads. So if you remember what I was telling you uh, yesterday about P threads and multi-threading, that's a library that's separate from operating system, but it actually does use operating system, or it does perform certain operating system, I guess, features, if you want to call it that. Now, the first breakdown for it is that this author here, Richard Stevens, he starts off with an introduction, but then in chapter 2, he talks about POSIX IPC, right, using the POSIX library. But then he also talks about System 5 IPC, where System 5 is a particular methodology for creating Unix operating systems. So now it depends on which of the actual um, libraries are, which of the actual libraries we're depending on when we use these features. And that would be implementation dependent given the operating system. All right. So now here, where he talks about the shared memory introduction, he actually takes a good 20 pages to talk about that, right? In fact, it's an entire chapter. When it comes to other things, there's something called remote procedure calls. I don't know if you've heard of it before, but you have functions that can call other functions. And with a remote procedure call, basically, you're calling a function for another machine that you may not even be connected to. So imagine exposing an API that allows you to communicate with some foreign or distant entity. Now, that foreign or distant entity could be another machine, or it could be another process, right? Now, if I were to take a look at this here, operating systems, this is the opposite book. uh, yeah, let me just, I have the blur on a bit. I'm sorry. Yeah, so this is the opposite book written by the same book author that you see in the Dropbox, Andy Tannenbaum, but this is the one with the actual source code and operating system in it, right? So here's what he did in the case of Minix. I'll just look it up really quickly and tell you about it. So in the case of IPC, let's see what he did. Inter-process communication in the Minix operating system. Okay, so in pages 120 to 122, let's just see. And for this, he's actually going to talk about his operating system and what he did. So he says that he uses apparently primitives for sending and receiving messages. Okay. And in his case, he says in Minix 3, function keys are used to send triggers to debugging. And what else? And then let's see, does he say anything else? I'm sure he does. Let me just make sure that Let me make sure that I'm actually getting the full scope of how he does this. So apparently he has his own libraries. All right. Um, he makes no mention of POSIX or SV, and I wouldn't expect him to when it comes to System 5 because that's a Unix standard, and this is Minix, which is not Unix. Other things that he says, however, is in the case of message passing, which it sounds like that's also what you're asking me about. On page 85 to 88, he discusses it to some degree. So let me just take a look at what he has to say about his operating system and what he did in that case of, you know, actually doing inter-process communication um, and handling it. Right. So he has a producer consumer model. His message passing in his case. Okay, so here's what he does. He actually, in page 87, he has a code sample, right? And in the code sample, he actually has a function called producer, and producer has an integer called item and also a message M. Now, message M is a message buffer, okay? Then from within that particular function, he uses a loop that is potentially indefinite. And what he does with the loop is that he uses the send and receive, and he uses an address for the message buffer. And with that, in the send and receive part, he then puts the consumer in there. Now, with consumer, he also has a consumer function. All right. With a consumer function, it's similar. He also has the item, and he also has a message M. He also has an index I. And in this particular case, for the consumer, what it does is that it moves between um, boundaries in which you would have, I guess, n different items that could be um, worked with, right? So then he uses send and receive again in that particular case for the consumer, but in the opposite direction, he throws in the message buffer or an address to it, as well as the producer. And so he uses his own API called back and forth, producer, consumer, and an actual message buffer where he basically just uses, the ampersand on his variable, which is a reference to the address space. And he then, copies over from the address space to the recipient or receives from the recipient into the address space back and forth. So that's how he does it there, right? There are other, let's see, since I'm here at home and I can just start reaching for stuff, I do have the FreeBSD book, and I believe I can, yeah, I can see what they do there really quickly. And then I can show you like some of the libraries that are online that go outside of operating systems, right? So just by going into the FreeBSD book here. So with FreeBSD, this is the first edition of, well, actually, it's kind of like the second edition is the third edition, but at first it was the design and implementation of the BSD operating system. This one is the design and implementation of FreeBSD. There's a second edition currently out. In fact, if you are like wondering about that, um, I could just say something like, right up here, uh, McCusick, another operating system book. Uh, Let me just put in BSD. Okay, so this was one of the earlier ones, 4.3. There was a 4.4. This is the 4.4 one. The one that I have, okay, I kind of have that one, but it's in English. So this is the one that I have. And here was the update that he made some years back, 2014. I got mine in about 2007-ish. Right. So I didn't know what was still on the way. But here's what it says about FreeBSD. The inter-process communication. And the good thing about this compared to Linux is that this is a full-blown operating system. So, there's going to be some actual details about the entirety of the operating system, not just a kernel. So in this particular case, let's see, connection setup for inter-process communication. That sounds exactly like what you're asking me about. All right, so it goes from page 455 to 463. They have part on connection setup and the data transfer. So I'm just going to turn there and let you know. Let's see. So the connection setup, in this particular case, they're going to create an association between sockets and the connection of sockets. Network sockets, basically, that's what we use for the internet, right? And the network socket is, like I said, a file that you can write to that you can share across machines even. So you bind to a socket, but you connect to an opposite address, right? If I am a server, I have a socket that I can bind to, but I need to, if I'm a client machine, I don't bind to an address, I connect to one, right? Now there's going to be a listening possibility. I'll put it that way. This has been a full-blown function definition. So he's just saying that these are the parameters, right? And then there's an operation of a socket layer that establishes connections within the operating system there. What this means here is that you're clearly going to have a um, a, a prearranged library system for networking, and they're using that for inter-process communication. All right. But this is not the System 5 version, right? And it may not be the POSIX version either. This could be their own in-house one. As a side note, BSD, Berkeley Software Distribution of Unix, is also the same Berkeley that created BIND, the Berkeley Internet Network Domain. And so Berkeley sockets are, a group of software network sockets unto themselves. But now he says the connection establishment in the client server model is asymmetric. It's not like, this back and forth in a peer-to-peer sort of way. And then he also says that the sockets are used to send and receive data. So this is different from what Tannenbaum did, in which he just had his own send and receive type of library functions. And then in the when you have a socket, you can listen on that socket for, messages that come in. And when there's a message there, then you can pick up that particular um, piece of data, kind of like a mailbox, right? Where um, or even a post office where you can send and receive uh, mail, right? Now, as for the data transfer, it says most of the work is done by the socket layer, which lies in sending and receiving data. So in this case, the socket layer itself refrains from imposing any structure on data transmitted or receiving. So um, in case of BSD, they treat it as full-blown networking. All right. So we're stepping outside of the processes to some degree. Now, if there's some networking, that's IO, there could be an interrupt, because you could be sending it over a network, but maybe there won't be if it's not like if it's not like IO going to an IO device, maybe there won't be. As for Linux, how do they do IPC? Let's just see real quickly. I'll see if I can like just pull it up and then by means of that, answer the last of your operating system question and then like, just kind of get you to see that there's just different implementations of these things. So for Linux, they're IPC. And let's see, did they say which kernel number this is? This could be any of them, but I don't think that they would change it too much because they have, their system signals here. Um, the IPC mechanisms. Processes communicate with each other with the kernel to coordinate their activities, and Linux supports a number of IPC mechanisms. They use signals and pipes, but also System 5 IPC, which is the one that came from Unix. All right. So that's the one they use. It's not like BSD where they're using their own BSD socket, right? They're using the System 5 IPC, which came from Unix. And now the System 5, do they even talk about that here? Yes, they do. In the case of System 5, right, what they have are messaging queues. And then there's also things like semaphores and shared memory. Now, we didn't get into semaphores just yet, but you can send messages or signals that are, related to certain constants that the operating system understands within a particular, like numerical or constant related um, context, right? Kind of like if I say return 0 and everyone knows that that means return false. So if I say return 1, everybody knows that the 1 means true, right? So they have a series of operating system related constants that are not usually misunderstood and they are used to communicate the nature of messaging. Now, let's see. In addition, okay, so the IPC API that they're borrowing has its own types of constant setups. So they have objects in the system, which include an IPC perm. They were talking about permissions earlier and also having things such as authentication for messaging, right? Also, they're talking about passing things by way of reference identifiers to the kernel, and they use system calls for that. If you remember what we were talking about with system calls, those are low-level messages, right? Then there's also the idea that there has to be certain access permissions, and that's how they manage these things. And they're telling you this is not a straightforward index, but it requires some manipulation to generate the index. So there's going to be a little bit of extra details behind this whole thing. The messaging queues that they use, in this case, multiple processes can write messages which can be read by one or more reading process. Okay, that's an interesting way of doing things. So in this case, you don't have direct communication. Instead, you have basically a log being written out by certain processes, and they can be read by other processes from that log. Um, and even in that case, Linux maintains a list of message queues, which means that there's more than one of those. Okay. So it's kind of like how you also have with process queues, they have a list of process queues as well. Uh, let's see, is there anything else? Uh, the case of semaphores. You know what? I'll save semaphores for when we actually do the discussion of it because it will be discussed like completely as a large subject. Well, or it'll be a subject unto its own self, right? But yeah, this is how they do it in Linux. Now, here's the thing. There are other libraries that also do communication, and there's something called design patterns, in which you have ways of building software. Design patterns, and this is lot of times in um, a lot of times this is in object-oriented programming, but there are ways that people build software for certain ways of organizing that software, not to be confused with, say, data structures, but instead, the way that software will behave or interact for a given purpose, regardless of performance time. Why I bring that up is because you have something called the or observable pattern. All right, observer. In this particular case, you have a behavioral design pattern that lets you define a subscription mechanism to notify multiple objects about any event that happen to the object they're observing. All right. This is one way to actually communicate to other programs, whether they're objects or functions or so forth, so that they too can get those updates. And as for actual libraries that do that, I believe Reactive X does it. All right. It's an API for asynchronous programming with observable streams. And this allows you to actually, create messages and also to be able to take whatever streaming data there is and combine it so that you can, you know, combine messages together. Also listening for anything that is being broadcasted because you have an observable stream, which means that there are updates being, taking place between concurrently running threads. All right. So that's one way that, these things can also be accomplished. So, I guess my question is, does this answer the question to a satisfactory degree?
Yeah, I bet. I also learned some new things as well.
Okay, a bit. What else? I mean, I will like to go on about it, but the thing is that in that particular case, I can't guarantee that each operating system will do the same thing. And, so I can't say what library they're using. I can't say what mechanism they're using or under which situations they would use certain things. Even they're like, this stuff is not straightforward. We have to fix it up in a certain
Right.
way. Yeah. And so that's the part that makes you say, well, at least you got your options open. And, if you remember what I had shown you, let's say like MPI, right? They have their own send and receives as well. I believe Java also has stuff like that where you can send and receive in threads. And they just recently started a new message passing API within a newer version of their virtual machine. So, there's a lot of these new programming languages and APIs that are doing things just like that. I think Rust, which now can actually make kernel modules, um, they are doing something similar where, um, when they run things simultaneously, they actually multiply the messages. That way, instead of locking things up, you know, um, data can simply be accessed because they've copied it over, just like how Go does. They copy it over rather than um, making it a direct communication one to one. So yeah, that's what you have there. So let's see. Now that we've kind of discussed that part there, and I want to let's I want to be able to uh go back to, I guess, trying to conjoin this with the context of operating systems. All right. So here you have a Java example. And let me just see. I think this one, well, of course, it might be a bit dated, but I don't think it's, like horribly dated. As you can see here, they're setting up a new socket. All right. And I told you what a socket is. Now, this thing right here, see that 6013, right? So the 6013 is most likely going to be the socket identifier, the socket ID. Okay. Um, Now, listening for connection is as follows. With a client, they accept a connection, all right? With a server, they bind to a given socket. That's just in general for networking. If you want to know more about that, there's a book called, let's see, what is it called? I have it right here. Um, I believe it's, what is it? Programming in the, oh, here it is. Here it is. Definitive Guide to Linux Network Programming. They talk about how, yeah, that guy. They talk about how, the basics of programming with sockets and even how to create your own protocols with, like the Berkeley libraries that are in Linux. But beyond that, you know, when you have a socket, you have a socket ID. And when it comes to the listening part, that's going to be on the server. The server listens for um, requests. The client sends those requests, and then the server responds. Okay. Now, moving further down, here they're saying we create a socket and request, and okay, they use port 6013. I stand corrected. That was not a socket ID, it was a port. However, socket IDs are indeed integers. I should tell you that. So now once they make a connection, the client can read from the socket using normal stream IO statements. Okay. After it has received the date from the server, then the client closes the socket and exits. Now, here's what I'll tell you. They really kind of like rushed through that one. The print writer, I actually have used that with my class. You can use it to read and write to files. It's reverse one. I believe there is a print reader, but I believe there's another one that I actually like to use a bit more so. But there's a different library. They put in java.io. Okay, that's one. That's where they got the print writer from, by the way. And then the java.net is where they got the socket part from. I did tell you about the NIO, which is the non-blocking IO. Um, and that also could be a possibility. But either way, moving forward, on the opposite end, here's what they did. They created a socket. Okay, here's the address, the loop back address and the port number. And then here's what they do. You should have seen this one before. All right. This is kind of like the scanner, but instead you have an input stream. All right. And you've seen the input stream before because when you use scanners in Java, the system.in, that's actually the input stream object. But in this case, you're declaring a new object that is an input stream. So they get the input stream from the socket that was created. And then with the buffer reader, you basically um, pick off certain sizes a certain size of input from the actual input stream here. All right. So this is kind of like scanner all over again, but you're going to be pulling things from the input stream that was just created. Then they're creating a string, which is going to be a line of data. Okay. A string though. And now they have the read line, which will read until you get to the end of the line. And then they're printing it out. So now here's what they do. If you notice right here, they finally close out the socket. Why do they do that? Well, remember that we said that with the Unix type of philosophy, everything is a file, right? So the same way you would close your files out, you'll close the socket out as well. So now there were questions about, well, then how do we do IPC? Remote procedure calls is one method. In object-oriented programming, sometimes you'll have something called remote method invocation, which is similar. But now in the case of RPC, you're using it to actually try to um, use procedure calls on some machine considered to be remote. Now, by considered to be remote, does it mean it has to be a separate machine altogether? No. It could be that it is, say, two virtual machines on the same machine, but they're just running in a different sandbox, or multiple processes that are network capable, or it could actually be different machines. Okay. So if you had something like, say, a clustered server where the whole thing is one supercomputer, but it's networked together, you might still use RPCs for managing these things, right? Um, they discussed it briefly in 3.5.2. Let's just take a look really quickly, and then we'll move forward. So going back, might have gone back too far. Okay, so here they're talking about the mock kernel that I told you about earlier, the one that came from Carnegie Mellon that was originally in the different BSD operating systems before they moved away from, um, well, before they, kind of went from monolithic to microkernel. But anyway, a message is received using a message receive function, okay? And now it says remote procedure calls are now executed via message RPC, which sends a message and waits for exactly one return message from the sender. So now the RPC models a typical subroutine procedure call that can work between systems, hence the remote term. All right. So that's why we're able to use RPC to communicate between different systems, be they processes or actual computers. Now, in this case, they're going to talk about how they actually use network-enabled IPC, right? In contrast to the IPC facility, the messages exchanged in RPC communication are well structured and no longer just packets of data. So you have messages addressed to an RPC daemon listening to a port on the remote system, and each contains an identifier of the function to execute and the parameters to pass to that function. All right. So it's kind of like sockets again, where they have, a descriptor for whatever it is that they need to pass things back and forth through. But instead, they have a networked system. Remember, I told you about what the word daemon means in the case of processes. And basically, they're processes that will run in the background. Um, in many cases, they will run while the operating system is running. Um, so, they can start even while the operating system starts up and continue to run perpetually until it's turned off, right? So that's what they use to communicate back and forth. And then they communicate through a port by and by way of that port, they send message packets. All right. And that's the long and short of it to some degree. So now using that client server model, right? They're sending things back and forth. And so you could say that when one processor or one process uses RPC to communicate with another, they could pretty much use it in their own context, as opposed to, say, calling, say, the system call, right? This is not system call. This is networking right here. It's not to say that there can't be system calls, but with networking, usually focus on um, higher level message passing, and you let the operating system use its own its own analogous lower level, uh, its own analogous lower level equivalents to make the whole thing, a reality in the back end of it all, right? So there are, different constants used on the network end, and then certain constants used on the operating system end, and they may be equivalent, but you usually use the network API rather than the operating system API to do network programming. All right. A pipe basically takes from, and this is usually serially, but it goes from one process to another. And so, it would be the output from one process becomes the input for a second one. And that's that's the short way of putting it. There's such thing as a pipe operator in Unix, and it does just that. So moving further down, in the case of POSIX message passing, I told you that that was possible, right? But here's the thing. It's an actual API that is external to the operating system. I mean, you could include it as an actual, um, you could include it as an actual library. So I know that like I have it here on my Mac OS, right? Um, and the API, although it is, uh, although it is, imported into the operating system, it's not necessarily specific to the operating system itself. You can actually either implement it or get a copy of it elsewhere online. And it's it basically is meant to work alike on all the different operating systems that use it. All right. So they have different functions for that: message send, message receive, and message get. I believe this would be control, right? Message control, so forth. There's also a QID. So this is a mailbox name, and it's known as a messaging queue ID. All right. So there they have their own environment. This, however, would not be specific to just an operating system. It's an API separate from the operating system's kernel, or or I should say that even if it's in the operating system, it's not unique to that system. So moving further, that gets us to multi-threaded programming. Okay, I'm going to take a pause right here.